Sure am.
I believe this is from your team, Alex, at University of California Fault Displacement Hazard Initiative.
Mm-hmm.
So yeah, please feel free to jump in at any time and add any comments.
Well, thank you.
Again, students, please ask Alex any questions as well. So in your mapping, as we've discussed, you'll want to think about if the structures that you're mapping are either the principal fault of that fault system, or if they represent a distributed structure that may be some distance away from the main faults. So here's some definitions to keep in mind, and then I'll show some examples which will hopefully help you visualize these definitions in a little bit more detail. So principal fault is the main or principal fault at depth that breaks the ground surface. And there's a variety of ways that this principal fault can be manifested at the ground surface. And so the most obvious would be a fairly simple or curvilinear trace. But there's a number of other cases where we could expect that we have somewhat more complicated expression of the fault at surface, whereas at shallow depths, we only have a single main rupture. So for example, at the surface, in this case, we could get en echelon fracturing, anastomosing, branching, mole tracks, overlapping stepovers, flower structure, or some sort of warping. And again, I'll show some pictures of these on the next slide. And for distributed, the main key is that it's not on the main faults. There's some spatial separation between the distributed segments and the principal fault. It may have synthetic sense of slip, so the opposite sense of slip as the principal faults. May be spatially distributed, again, not along the primary, adjacent to the primary structure. And the fault segments could be discontinuous or relatively short.
Maybe I'll just jump in really quickly since you invited me to. On the previous slide there, some folks might be looking at the fact that flower structures or other slip partitioning structures are put under principal, and that one's a little bit tricky. You could totally argue it being under distributed just because it's kind of connected in a branching way to the main fault. It's admittedly ambiguous. This is kind of what made sense for the fault displacement project. But if if you guys need a different definition as you go along, just as long as it's clear, I think, in the maps that you put together, I guess recognize that a technical argument could be made against putting those guys under principal.
Yes. So here are these different examples of principal and distributed or secondary faulting. So in each of these cases, the red faults were identified as the major fault, and the yellow and blue segments were identified as the secondary faulting. So this first one is probably the most obvious case where you see a single through-growing fault that's curvilinear in some segments and relatively straight in others. And so in this case, it's probably fairly easy for us all to agree that this main fault here is the principal fault. As a side note, these are examples of fault ruptures, I believe from the Landers earthquake. And so what's preserved and what you see in the fault scarps from much older earthquakes will look a little bit different than what you see here. Here's an example where we see these en echelon fractures. And again, probably it's assumed that they all connect to a main fault at a shallow depth. Here's an example of branching where we get this, say, 50-meter wide zone of branching. And here it's imagined it's hard to identify any of these segments as having slip that is so much larger than the others. And so again, these would be inferred as a single broadish primary fault zone. And here's an example, essentially what Alex was just talking about. We have this trifurcated branching or flower structure. And my guess here is to call them all the primary fault. Probably all have fairly similar amounts of slip. And again, it's assumed that the faults all connect at depth. But in the case where you saw perhaps the slip on this main fault was much higher than the others, and therefore perhaps may be more likely to be preserved longer in the geomorphic record, then could also interpret this, perhaps this middle strand as the main fault. Does that sound appropriate, Alex?
Perfect.
And again, here we have this anastomosing structure where we have this 50 to 100 meter wide fault zone with these multiple segments that again probably all have similar slip and would be assumed to connect at a fairly shallow depth, perhaps scaling with the width of the surface deformation. So the question that you're probably wondering is, well, how do I know which ones are which? Which would be my process for assigning primary or distributed faulting? So to reiterate Alex's points, it depends. And so likely depend on the properties of the faults, the data sets that you're looking at, as well as the geologist's interpretation. And so it's important for you to justify what is your reasoning for calling a primary fault the primary fault or the distributed structures distributed. And we expect that people's answers may differ a little bit, and that everyone could be right, but again, we want to see how people define what makes a structure a primary or a secondary fault. So the process is going to be a little bit iterative, but at first you want to start, for example, qualitatively, what seems to be the most obvious primary faults, and how can you describe those terms? For example, you may want to look at the faults that are long and continuous and use those first to call your primary faults. And similarly, you may want to then look at features that are spatially separated from these main faults or discontinuous, and come up with a qualitative way of describing those. And then once you have those ideas in your mind, you can start to look in a little bit more detail at features. And this process then suggests an iterative approach where you look at these different criteria for calling features primary or secondary. Again, looking at whether things look to be, whether if they're spatially associated or not. for looking at these principal structures, you want to keep in mind that you can get these relatively complicated structures at the surface, whereas at depth, the say 100 meters or so depth, the ruptures that we see at the surface may join into a single fault. And so keep these different ideas of essentially faulting structural geology in your mind when you're assigning features to be either primary or distributed structures. And again, for the distributed structures, things you'll want to keep in mind at these later steps are if they're antithetic. So if you see an opposite sense of slip to the main fault, if you see cracking, or probably more likely for immediately after an earthquake than preserved in the geologic record, as you may see ground fractures that represent high degrees of shaking or shattering rather than viewing the actual principal fault trace. So that's the presentation on this distributed and primary faulting. Again, the key is to appreciate that your answers are probably going to depend on your work, includes the area that you're in, the properties of the fault, data sets that you're working in. Are you working from data from the 1960s or from last year, as well as your interpretations? And so it's just key for, as you're defining these different terms, to come up with a set of rules or justifications that you can use to explain how you came up with your exact ranking of whether features are the primary or distributed faulting. And we'll actually have a few readings for the rest of the semester, and one of them will be looking in more detail at primary versus distributed faulting structures for the Landers earthquake. So discussing that paper will let us dive in a little bit more detail about some of these topics.
Maybe one thing I'll add, as having done quite a bit of this for the UCLA project this year, it's tough, as you can expect. One field that we've added to the database that has been really helpful is a ranking or categorizing confidence flag. And I like just using 2 bins, like, oh, I'm confident it's principal, or I'm not confident. If you have 3 bins, everything gets dumped in the middle bin and it ends up being useless. So if it helps you feel a little bit better, if you're on the fence about something, see if adding a ranking confidence field alleviates some of that stress, and then might be surprised how things fit together then after you just get it down as a category and move on.
Great idea, thank you. Students have questions, comments, confusion?
I have one more comment to add. This is Rich, and there's a lot of terms: flower structure, branching, whatnot, and some of you are kind of new to these terminology, so that in front of you, or out, or just have terms at the ready, so you're looking at the map. What this is second what, then you can look at some of those terms and say, oh, okay, I think this looks like a branch or something. So just keeping the terms at the forefront will help you as you're mapping and determining what to make each line.
Also, so I put on the web page this doc. So if you go to our course webpage and then fault mapping notes, you'll find this or a similar document with a little bit more information here where it says primary versus secondary faulting. And that will get you this document. So you can refer to this information very easily while you are mapping. And here are the different examples of primary and secondary faulting.
One small thing just I noticed here is that in general, this is, or I think you had spoken about this a little bit, Chelsea, but the mapping scale is going to matter. So these left ones are, 1 to 20,000, 1 to 25,000. But as we go to the right, which shows sort of increasing complexity, the scale is getting larger. In other words, you're zooming in. So that's, I think, why Alex, for example, was bringing up scale is so critical, and why we kind of keep talking about it. And that's why probably for the group, for the students, that's why kind of being sensitive about scale, maybe trying to map at a consistent scale will then give you sort of consistent representation of this kind of ranking. Because, if you zoomed in close enough on the figure 2A on the continuous trace of landers, you probably would find that it might be a little bit more distributed and echelon and look like figure 2C, but you just can't see that because you're backed out. And so there's this kind of a representation dependence on scale. So and then also just, I think people shouldn't feel a lot of pressure like you have to find primaries and secondaries, especially in these environments. It's easy to do it after the earthquake occurred, but beforehand, it might have been a long time since the last earthquake. So one of these associated issues, right, is that the secondary traces are not often preserved as well. So we might not see them anyway. So don't force it, but you might see it. And if you see it, then you want to account for it.
Yeah, and then just one more comment kind of along those lines is, the geomorphology that's created by faulting, it kind of occurs at all scales. So historic ruptures that we've seen in some of the presentations gives you an idea sort of the pattern of how these things go, the patterns exist on the main faults, the features might be bigger and whatnot. The patterns are generated. So it kind of gives you an idea looking at the historic detailed ruptures of what kind of the longer term trace might look like in the landscape as well.
Do the students have any questions?
Will there be a uniform symbology across the board for all the students, like everyone doing the mapping, or is it independent?
Right now it's going to be independent, unless Alex, are there suggested symbology that you know of?
No, unless it matters for you guys on the grading side of things. I think there's actually a lot of value in having it be independent. You can, instead of kind of forcing things to fit into a mold, you can figure out what makes most sense for your area. And that's actually how standards get set and improved, is people being independent. So that's good, I think.
Great, thank you. So we have a few minutes left of class. If students have any general questions about their project, this is a great time to ask.
I do have a general question.
Yes.
So I've got, like a project 1966. Where is the best place to go looking for that data?
The USGS Earth Explorer.
Earth Explorer. Okay.
And
I was on the USGS site and I was like, where is that? But okay.
So it should be the same place where you got the homework, where you
Yeah,
went for your middle homework assignments to find the data.
cool.
And expect nothing will be georeferenced.
Yeah. So then that's another question. What is the best way to I don't know, zoom into my area without really looking at Google Earth, you think? Just searching.
So you will have to look at it to find the images at the Google Earth level. Or so I forget if Earth Explorer, if it looks like Google Earth or if it's more of like a simple base map that you would, for example, use to drive, or you might see roads on. So if you can only see the satellite imagery, see if you can turn that off and see the road map to select the areas. But otherwise, I think you will have to look at the modern day satellite imagery.
Just not look too close, huh?
But for a lot of the areas, if you are all zoomed out, you won't see, and probably then especially will not remember where you saw any of the ruptures.
Gotcha. Thank you.
And Ramon and Rich, do you have any more advice on that?
That's tricky. I think with, trying to do as much as you can from a traditional map base that's, like you said, that kind of used for navigating on your phone or whatever to drive somewhere. So you don't see imagery, and use that to sort of get located geographically and only in a kind of last resort turn imagery on. I think we just want to keep talking about this because you can imagine, right, when we write this report up, we want to be able to say with a fair amount of confidence, that these maps were produced with minimal or with no or with limited awareness of the earthquake rupture patterns. And so it's kind of like, to me, that's the critical thing is to really honestly be able to say that. And that's why I keep emphasizing it, because I'm just looking forward to how we present our experiment. So it's not meant to be annoying. It's just like, how can you do it so you can sort of preserve that? Because bias is so powerful. Like, as soon as you have a hint of where something is, you can't unsee it. And we just want to, that's the whole point here, is to try to not have that bias. And so you just have to protect yourself, but we're not trying to make this so annoying and impossible. So if you get stuck, just kind of reach out to us maybe before you break down and figure out where it is based on the post-earthquake rupture. So just preserving psychology, preserving unbiased perspective is hugely valuable. You guys have this special characteristic of not having seen these things, so but having geological skills. So it's actually kind of hard to have that combination. So we don't want to be annoying, but something cool that we can do here.
This is maybe biased knowledge, but I know in Parkfield, the ruptures are not super obvious on the modern imagery, whereas for other data sets like EMC or Boar Peak, they're much more obvious. And so we may also give different instructions for people with different earthquakes or mapping in different areas.
Good to know. Thanks for that.
would you like us to be including any geomorphic features at all on our symbology, or leave it strictly to fault features?
So in the assignment, we ask you to spend 2 hours or so mapping very detailed in a fairly limited area. And so you could either do the morphology or different geomorphic units, depending on what type of data set and area you're mapping. And then after you spend those 2 hours, then it's up to you if you think that you generally understand the context to the area and you maybe don't need to map in quite the same level of detail everywhere to map the faults well, versus if you think that you actually do need to map things in extensive detail, then you should. So it's, again, it's up to you. After you spend those first 2 hours doing the very detailed mapping, and if you decide that you do need to continue with this detailed level, again, it's not a race, and we prefer that you have a very high quality map over a shorter area than a low quality map over a longer area or bigger area.
Yeah, I'll just add, it makes me uncomfortable to some degree to just see you guys blowing lines along that are just the faults without having sensitivity to the other features, basically the quaternary geology and the morphology. So I think what Chelsea has said is quite accurate, is at a minimum, you've got to spend some time mapping so you're training your brain. But to me, it's maybe kind of personality wise, it's sort of being systematic would mean progressively mapping the markers and then making the interpretation of the fault traces, just kind of to be thorough. But as we know, experts tend to, experts just see it, and you guys are becoming experts, so you just blow through. But I don't know, to me, it's a potential for greater bias. It's a potential for being less thorough and even in your coverage. Remember my whole thing about, one thumb, everywhere on the map. So in a way, making sure you checked somewhere means you might as well map there. So you just say, oh yeah, well, that's a fan, and this is a channel margin, and oh, what's this weird hill here? Oh, that's the fault goes through there. So it's modeling that sort of process of kind of objective to interpretive activity. But I don't know, I'm kind of stuck in this world maybe too much, and that might make you go too slow.
Well, just remember, we talk about a trail of breadcrumbs of these geomorphic features along the fault, and it doesn't take a whole lot of extra time to have just a point layer or something as you're going along, and then it just keeps track of where where the fault might be. So just think of that trail of breadcrumbs and being systematic going along, and you don't have to map every single geomorphic feature, but enough of them that you're gaining confidence of where it might be.
If you have questions or you want to discuss how you've mapped in the past and then how to map going forward to any step in the process, then please come and talk to us.
Well, we have a pause really fast. Just a quick question on EMC. It's already been georeferenced with that LiDAR data, correct? So it's pretty easy to already get started from what I see.
Yes, and so all the topography on Google Earth, on Open Topography has already been georeferenced. And so if you want to start working on the topography, then that's fine. If you want be working simultaneously on the optical imagery as well as the topography, then that's also fine. Probably my guess is you don't want to get too far into your mapping before you look at both data sets.
For EMC, it only has that LiDAR data on the Google Earth. Or for the open topography, do we need to go get the Google Earth imagery now, if I understand that correctly?
So remember, Jesse and Bell used both the images, and they learned or made quite different types of observations from the topography and the optical imagery. The other thing you'll notice is the EMC topography data is about 6-meter resolution, which is really not that great. For example, they were mapping at 2-meter resolution, which is okay. And so you'll want the higher resolution, but also the optical imagery to help you on your mapping.
Now, if we were going to pull up the Google Earth imagery, you would want us to go back in time and use like the one, like say for the LiDAR image I have is from 2006. It would be preferred to use the 2000s around there, Google Earth.
So you can use any data set that was prior to the earthquake. And so in most places, you get more and better quality imagery with time. So that earthquake was in early 2010. So anything before then is acceptable to use. It does not need to be at the same time as the LiDAR imagery.
Thank you for that clarification.
And I guess the other thing is, talked to Belle earlier, and she said one value of even the older images is to go back and try to identify what is human versus natural for later things that they were unsure of. So you can also use that clock button in Google Earth to go and look at a wide set of imagery just to see how things change and what they look like, even if we don't georeference everything for you. So if you, for example, see a feature in later imagery and you're not sure what it is, look at the older imagery and discuss whether or not you think it's tectonic. You may want to leave a note or comment saying that you accessed the older imagery and that confirmed some hypothesis that you had. So the point is everything before the earthquake is fair to use.
Thank you for that clarification.
It's almost time to go, 10:25. And
Yes.
this might show my age, guys, but you know, there's this Ferris Bueller's Day Off, and remember how it was like anyone, Bueller. We're trying to get you guys to ask questions. So anyone, Bueller. So it's just a joke. Don't be shy. Ask questions now or later.
So we're coming to an end. Tuesday, attendance at the beginning is mandatory. Bring your questions. We won't have any lecture planned. And questions can either be generally about the project or things relating to your specific area. And we'll talk a little bit at the beginning as a group. And if you don't have questions, you can also go and continue mapping, come back if you have questions, and so forth.
All right, sounds great.
Okay, thanks everyone.
All right, bye.
Thank you.
See you later.
Thank you.
Oh, hey, Chelsea, real quick.
Yes.
Sorry. I think I might not be on like the class listserv or anything because I don't think I get like any of the emails. And I also don't think that the Google Drive was shared with me because I got your last email, but then I didn't get an assignment or I can't find the Google Drive for all of the shape files and stuff.
Okay, 1 second. You're correct that